Okay, picking back up with example 2, we solved for our interval. We know that x is between -2 and +2, but we're going to have to plug in x values, those endpoints, to see what's happening. If I plug in x equals 2, guys, again, what is very, very helpful is to start with the positive termed series. If I plug in -2, by the way, I'll get -2 to the n divided by n plus 1 times 2 to the n. Generally, what you will see is one endpoint. When you plug that specific value of x in, you will get a positive termed series. And generally, when you plug in the other endpoint, you will see that you actually get an alternating series, pretty much the same formula, but alternating. Now, right now, kids might say, I don't see an alternating series. Here's my question to you. Let's look at this -2 to the n just off to the side. -2 to the n divided by 2 to the n. You might wonder what that is. Well, look, both of these are raised to the n power, so I could say, well, hey, how about I just write it that way? Just take that whole fraction and raise it up to the n. And what is -2 divided by 2 then? It's just -1. Wow, this thing right over here is -1 to the n over n plus 1. Now, of course, we have our two series right here. This first one works out a lot nicer. Looks just like so. What I want you to do is always consider the positive term series first. Here's why. If that series converges, let's hypothetically say it did, you're going to be delighted when you check the second one. Because then the second one you could say, oh, so you're saying when I put absolute value around it, I converge. In other words, when you check the positive term series first, and if you get convergence, you're showing that the second series, the one with the alternating, is absolutely convergent. And if a series is absolutely convergent, then it converges without absolute value. You're saving yourself work. Now, this is not going to happen right here, sad to say. Believe it or not, let's still check this first series right here. This one in blue. Very famous series. Very famous series. Kids might look at that and say, I don't know about that. Yeah, it is a very famous series. Start writing it out term by term by term, maybe. Maybe that's sometimes what kids might think about doing. I'll do that off to the side. Plug in a 0. You get 1 over 1, that's a 1. Hey, plug in n equals 1. You'd get 1 plus 1 is 2. You'd say, oh, that's a half. Plug in a 3. N equals 2. 2 plus 1 is 3. You'd get 1/3. You get the idea. What does that look like? It is the harmonic series. Now that can really bug kids and drive them crazy. They'll say, no, it isn't. Mr. Dobner, look off to the side. The harmonic series was this. 1 over n. Yes, when it starts at 1. This one is starting at 0. If you're starting at 0, if you made a change at your counter at the bottom, you'd have to accordingly make a change inside of that formula. But look, you would generate for either one of these. Check it out. You're getting the exact same thing. So there's this cosmetic change when you start at n equals 0. But what are we seeing? This is a divergent harmonic series. Yeah, like as long as and we talked about that before. Yeah, even if you'd start it at 10, it's still going to be a harmonic series. You just lost those first few terms, however many. You're right. Good. Take a look at the second one, though. What type of series is that? This is an alternating harmonic series. Yes, this is a convergent alternating harmonic series. Now, of course, you still could do the alternating series test, but this series is the most famous alternating series of all, the alternating harmonic. We may, as a statement of fact, say that it converges. So at the end of the day, as we look at this, you can say, well, wow, -2, that worked. +2 did not. So this is your interval of convergence. We always put square brackets around a number that we may equal, open parentheses for one that we cannot equal. Now, understandably, I think sometimes kids are looking at these problems and they begin to fear that all of these problems must be a tremendous amount of work. And that's not always the case, thank goodness. Let's very quickly take a look at example 3. For example 3, we've got a ratio test that we're going to have to go through. The limit is n goes to infinity, and we can say the n plus 1 term, that's x to the n plus 1 all over n plus 1 factorial. And of course, I can divide by this nth term, but it's just as good to divide saying that it's multiplying by the reciprocal of the nth term. So we have this, and this is so much easier. We can say x to the n and x to the n plus 1. That leaves us with one more factor of x up on top. And hopefully you remember how to cancel out down below this n plus 1 factorial. Well, it's n plus 1 times n factorial. You might remember a little factorial trick that we can do. Why do we do that? You can cancel these n factorials out. So now we can look at this and say, well, this is the limit of the absolute value of x all over n plus 1. And I hope you can see the n plus 1 I pulled out of the absolute value. N is a positive number anyway, so we don't need to keep it there. We do need to keep x in our absolute value. But here's another important thing. Guys, x is a real number. X, by the way, could not be infinity. Infinity is a concept. It's some real number. It could be numbers like 1, 2, 3, -5, things like that. Could be decimals. But help me out. This limit, as n goes to infinity, n plus 1 obviously is going super, super large. Our denominator is headed towards infinity. What's going on? Absolute value of x divided by something super large? That should equal 0. I don't know what x is, but no matter what value, real number I have, when I divide by something unbelievably large, that has to go to 0. Wow, that means that we get convergence everywhere. It converges for all x. Interval, if they ever said write out an interval, you'd say from -infinity to positive infinity. Okay? So that's a wonderful type of situation. You can see we really didn't wind up doing nearly as much work as some of these other problems. By way of comparison, let's take a look at example 4. Once again, we're going to do a ratio test. And oh wow, we use this ratio test so much. Here's your n plus 1 term. And then we're dividing by the nth term. And here's a perfect example where it's probably just as easy to vertically stack those terms. You don't have a complex fraction. But we can see pretty quickly, again, some similarities. One more power of x up on top. And with the n factorials, here we go again. You know, the n plus 1 factorial, you can write that as n plus 1 times n factorial. And happily, you can see that the n factorials are going to cancel out. So it doesn't take too much work to see, yeah, you still have an absolute value of x, but then you've got n plus 1 coming out. Now, forgive me, I forgot to write the limit here. I'm going to do that real quickly. Don't want to forget that. So the limit as n goes to infinity of this. Where are we headed? Towards infinity. With one exception. There is one surprising value of x where this thing actually wouldn't go to infinity. 0. And sometimes kids will say, whoa, we talked about this in L'Hopital's rule. Infinity times 0 is indeterminate. Oh, that was when you were just getting close to 0. This is being very different. If x equals 0, not close to 0, but if x literally equaled 0, this sigma would become a very funny looking kind of a formula. You'd have n factorial times 0, and oh my goodness, 0 times anything just wipes out. You'd forever add up to 0. 0 plus 0 plus 0. This will be convergence. It converges for x equals 0. Now that can sound so strange. You're always going to get at least one value of x for which you will converge. It's called pointwise convergence. Many professors call it trivial convergence. Trivial convergence in the sense that you're always adding up zeros. And it's not all that exciting. You'd say, well, of course, if I add up 0 forever, I'm going to converge. Well, that then leads us to the next page. And I just wanted to point out to you that you have this wonderful theorem right here where, look, if you have a power series, we're going to say that a to the n, x to the n right there, x raised to the n, is centered at x equals 0. And that can sound so funny. It's not too early to begin talking about where a power series is centered. If you look right here, whatever x is being subtracted, if you have x minus a number raised to the nth power, that's where you are centered. Why do we call it that? That's actually where you would get trivial convergence. That's where you'd say, when I plug in the appropriate value of x to cancel out where you are centered. If you're centered at 0, you let x equal 0. You will always get that value of x to converge. What else could happen? You could get an interval. And if you saw negative r to r, guys, you're going to see that in the center between that interval there would be c equals 0. That would be a centered value right in the middle. And that's another reason why we say that you're centered there. Any interval, the middle of it here would be 0. Maybe both endpoints are going to converge, maybe only one, maybe neither. And then finally, a third possibility that you might have, we saw this earlier, you might find that you converge for all values of x. That would be going from negative infinity to positive infinity. Now we're going to skip number 5. just so that we can take a look at a following theorem.